So we are gonna get started with we're gonna get started with a project. You know, basically, let's just try and remember the goal for these was to learn quantum mechanics from the ground up, right? Like, it's not about the physics project, but it's about getting into quantum mechanics and kind of like doing it in a way that it's kind of a bit more dangerous, I'd say, right? Because this whole project just might end up not being the right thing in general, but at least it's going to challenge me with the learning that I'll be doing, right? Um, I don't know where to start, to be honest. So there's a lot of stuff in here. Let me maybe start by tweeting, actually. I go to the dashboard here. Let's see. How can I share? Yeah, actually, I don't. So I can. I think I can just tweet that directly. So getting started with Wolfram physics project. So basically, was it twitch.tv/ come on / uncertainties. There you go. Cool. So today, in today's session, I'm planning to kind of spend an hour on these, at least today, is to basically, oh God, I think I gotta get some nice headset with maybe noise cancellation or something. I don't know, we'll see. Um, I don't know, try to find a way to get started. Remember, what I'm trying to do is, the goal of these, kind of project is to learn quantum mechanics. It's less about the whole, the entirety of the project. It's more like I wanna try to see if I can, just by taking a look at this project, learn about quantum mechanics in a way that I have to constantly be careful and constantly challenge what I'm learning, right? Rather than just taking a book where I know that this is the standard stuff that it's being taught at the university, or taking a course or whatever, right? To kind of get a bit of a more hands-on approach. Um, so where to start? I mean, there's definitely software tools. There is the technical introduction, and I am a little bit familiar with the basics of this project, but I might as well jump to, instead of just going through the basics and all this stuff, which I'm a little bit familiar with, but I might as just well jump to, I think it was here I saw quantum. I hope you can read that. If not, I'll try to zoom this in. Probably better. Probably better this way. Um, Oh, basic concepts of quantum mechanics, quantum formalism, quantum measurement. Okay, so there's actually, some stuff in here. Quantum formalism, basic concepts of quantum mechanics. Maybe that's where I should start, just by taking a look at these. And then, if need be, kind of, go back to the first chapters, which I might have to do anyway, right? Let's see where this takes me. So this is one thing. Then this introduction to Wolfram physics project tools and functions. And I found this last time in the first session I did, and this was a bit of a hands-on thing, I think. It's an actual clickable thing. It's a Wolfram notebook. Do I have to install anything? State-of-the-art notebook interface with the world's most productive programming language, scalable for programs from tiny to huge. Oh, so you can sign up for free? The basic plan? What does this do? So let me just open this again. I might just sign up later. So why is my internet so shitty? Come on. Don't do this to me now. Really? Or is this is just not working? It's probably my laptop again. Oh, come on. Mm. Does this have to happen to me every time? Can I just always open Google or something? Not Gmail. Google. Okay. Okay. So there seems to be something off with Wolfram Cloud. I wanted to take a look at the notebook. But okay, I can do this later. Um, let's start here, right? So it's chapter 8. I mean, before that, there's introduction, basic forms of models, typical behaviors, limiting behavior, blah, 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 the updating process. So, I mean, all I know from the basics is that essentially the concept is you have this hypergraph, um, and then you have rules, right? Um, and this is a German message. Okay, no problem. So basically, yeah, have fun. Cool. Anyway, let's just focus. It's a bit late, but let's just focus. Mm, anyway, so the idea is you've got the hypergraph, and then you have updating rules, right? That tell you if you find these patterns in the hypergraph, replace them with these other patterns in the hypergraph, like nodes and edges and whatnot. Like if you find this node connected with this node, replace it with another thing, right? So you have these things, and then the idea is that certain configurations of these will basically, if you evolve them for a long time, they'll generate structures like hypergraphs that like somewhat resemble um, space, I'd say, right? So um, manifolds of some sort. I don't really know what the right naming for these is, but like the idea is that the rule evolution, the evolution of these hypergraphs is time, I think, and then the whole model, the whole hypergraph is actually space, and then there's certain models and certain sets of models and rules that exhibit certain properties that allow certain physics concepts and laws to be mapped into this model, right? Like special relativity and things like these, which I have absolutely no idea about, right? So the idea is that you have this very simple model you can map for certain models. You can actually, or for certain pairs of initial hypergraphs and rules, you can then kind of map physical known physical phenomena, known physical laws to these. Um, so, this is something that I might come back, I guess, at some point, because I'm assuming I'm not going to be able to learn everything that I want to learn from, I'll get stuck probably fairly quickly, because that seems to be like it's chapter 8 of the technical introduction, which is basically the last chapter. This is additional material, so we'll see. Come on, if these things would just load, that doesn't load. I can't believe it's definitely not me, right? I can go to Twitter. That just loads perfectly. Okay, cool. Doesn't matter. I mean, it still takes a while, so it might be on my end. It might be on my end, but let's go. So, um, and here we have basic concepts and then quantum formalism. So quantum formalism is okay. I should just uh, basic concepts of quantum mechanics. Quantum mechanics is a key known feature of physics, and also it seems a natural and inevitable feature in our models. In classical physics, or in a system like stellar automaton, one basically has rules that specify a unique path of history for the evolution of a system, but our models are not set up to define any such unique path of history. Instead, the models just give possible rewrites that can be performed on hypergraphs. But that's what I was saying, yeah. But they do not say when or where these rewrites should be applied. So this means that, like the formalism of quantum mechanics, our models, in a sense, allow for many paths of history. So I guess what they're trying to say here is that because there's different ways you can update a hypergraph, that these different ways could be what you would usually one way that you could see kind of the whole wave function story, right? Um, of being in a superposition or being in an entangled state, kind of. Um, there is, however, ultimately nothing non-deterministic about our models, although they allow many different sequences of updating events, each of which can be viewed as different path in history. The models still completely determine the overall set of possible sequences of updating events. Yeah, if you can keep track of all the possible ways you can apply these rules, then you will end up with a at least the set of all possible um, hypergraphs you can adapt with after applying all the rules, right? This is the um, oh, look at this, it loaded. Okay, let's see if we can actually, because I think this might be, for those who are not familiar with this concept, might be a bit better if we start with these. Because as I said, I think I know a bit of the basics, but I'm not so sure. Can I zoom in here? Yeah, I can zoom in. So this computational essay is intended to help you get started exploring Wolfram models. So this is the software tools part, and then we'll go back to this in a second. Okay. So this document is a notebook. You can run it directly in the cloud by making your own copy. You can download it to the desktop for use with any Wolfram language system, Wolfram 1, Mathematica, Wolfram Programming Lab, or free Wolfram engine for developers. I have to check what is they accessible for free, because I'll definitely maybe the cloud seemed to be a good option. Once you have your own copy of this notebook, you can edit any input, then evaluate it using Shift and Enter, and then you'll see many objects here that look like these. These are functions that are automatically accessed from the Wolfram function repository. To use them, either copy or type resource function Wolfram model, etc. For a full list of functions related to Wolfram physics projects, see the list of functions. So there's an actual list of functions that have been developed for these specifically, or click the plus to get to documentation, blah, blah, blah. Note that technical introduction and announcement only are clickable and provide code that can immediately be run in any Wolfram language system. The Register of Notable Universes also contains a notebook for each universe. All code, I guess what they call a universe is these, as I was saying, like an initial hypergraph and then the rule, the updating rules. But let's go. Okay, so let's start by looking at a few steps of evolution for a particular rule. So okay, so this is a Wolfram model, and this is the part that if I once I get that running, either locally or in the cloud, then I can edit that, right? I guess what this is doing is, so it's painting these things as hypergraphs, or are these rules, or what are these? So x, y, and x, y, x, z turn into x, z, x, w. XZ, XW, YW, ZW. It's a transfer. It's okay. So these are these rules or what are these? So evolve for 5 steps from a self loop. I'm not sure I understand these. Mm. Know that the very first time you run a Wolfram model function on your computer, there may be a small delay while this definition is automatically downloaded and set up. The structures we're getting here are representations of space in a very tiny universe. We can make our universe slightly bigger by going 10 steps. Yeah, so these are 1, 2, 3, 4, 5, 6. Well, that's the initial, I guess, and then 1, 2, 3, 4, 5. And I guess this is just a copy. These are the evolution. So this is the initial state, and then it says x, y, x, z, x, z, x, w, y, w, z, w. Like that, I could see how. Oh, okay. So these are the rules, and this is the initial hypergraph. 0, 0, 0, 0. So I guess each of these brackets is an edge that goes from a directed edge that goes from the node 0 to the node 0, and another one that goes from node 0 to node 0. So that's the initial state. Okay. And so then these rule, okay, so and then this is just one rule I see. Okay, so the rule says if you catch this pattern x, y, and x, z, um, and then turn it into these, which basically it's adding a new. So it's keeping x, z, skipping one of these, right? X, z, and then it's doing x, w, y, w, z, w. So it's introducing a new node w, and then it's pointing. Oh, this is all clickable like this. Okay, cool. And then it goes from here to here. How's that? It doesn't touch this one at all. This is x, y, x, z. X, Y, X, Z. Okay, so for each pair, so no, that's complicated. Okay, that is complicated because then this would mean that it maps. I'm not so sure I understand really what this is mapping, to be honest. But I assume this means that this is one of the edges and then another one. So you kind of basically have this rule applies many times, right? Because you kind of the pattern of turn these two edges into these four edges essentially means that you're introducing, for each of these two nodes, you're introducing two more nodes. That's why we have four nodes. Okay, cool. Yeah, it's complicated. And then you get this beast. Let's take apart this example a little. Okay, cool. So okay, so this is the update rule that we're using. We can make a graphic representation of the rule, make a graphic representation model of the rule plot, and then the Wolfram model. Uh, yeah, so the rule says if you find these, then turn it into these, which means you're adding a new node, and then you make an edge that points from all the alt nodes to the new one, and you keep this one. Yeah. The objects on which the rule operates are collections of relations represented as lists of lists. Give the state produced after 3 steps. Final state, that's the state. We can then represent these collections of relations as hypergraphs, or in this case, a graph, right? Because they are just, the edges are just connecting two nodes. Vertex labels automatic. You can convert collections of relations to ordinary graphs. If relations involve more than 2 elements, it won't be a completely faithful conversion. Once you have an ordinary graph, you can use any of the many standard Wolfram language graph functions. Graph 3D, hypergraph to graph, Wolfram model, rule, final state. You can also try to reconstruct a 2D surface. Try to putting webbing on the 3D graph to form a 2D two-dimensional surface. You can make measurements. You can make measurements on the states produced by Wolfram models. As an example, you can compute the sizes of neighborhoods of successive larger radii around each element. Compute the average over all nodes. Graph neighborhood volumes. The flat part gives an estimate of effective dimension for the space corresponding to this state. Oh, actually, that is a pretty big notebook then, I think. That was the first one. Okay, cool. We just saw how one can get explicit states or graphs from Wolfram model, but it's also possible to get a purely symbolic representation of evolution. Indeed, this is default. Generation stand events 482. Now you can ask for specific properties of the evolution object. Okay, so this is really already goes deep into the actual models and how to manipulate them and all that stuff. Multi-way systems. Okay, so you can actually see the stuff that's been newly created or something. And these are the different probably ways you can apply the rules. And that's the multi-way system, I think, if I remember well. Okay, but that does not take me anywhere at that point. I thought that would be a bit more. No, that's, I mean, I thought it would just be really intro in like at the intro level, but that's actually, that goes a bit deeper. Let's see. I mean, at some point I'll have to start getting into the weeds of it, but let's go ahead. Let's go on with these. So, um, So there is, however, ultimately nothing non-deterministic about our models, although they allow many different sequences of updating events, each of which can be viewed as a different path of history. The models still completely determine the overall set of possible sequences of updating events. And indeed, at the global level, everything about the model can be captured in a multi-way graph. That's, yeah, so this, I think this is the graph that basically plots all the different transformations you can get by applying the different rules, right? Okay, like the one below, with nodes in the graph corresponding to states of the system. Here, for simplicity, a string substitution system and every possible path through the graph corresponding to a possible history. So you start with A. So in the start, and then I guess A, AB, then AA, ABB, So there's some sort of rule that's being applied, and then I guess this rule here is turn A into AB, right? Because that's the first step is just really deterministic. But now, um, okay, so there's more rules here, I guess. There might be another rule that turns a B into an A, right? Because that's kind of what this branch is doing. But then this other path here is applying the first rule, which turns the A into an AB. So you kind of have two possibilities. Either we apply one rule or we apply the other rule, right? So um, what would be the analog like if that would be a quantum system? I'm thinking. Would that be the analog of like a Bell state, for example? You have a control knot, like a Hadamard in superposition, the control knot, and so you're with the Hadamard and the control knot, so you're like either your system is in the 0, 0 state or in the 1, 1 state, so that would be two different branches. Maybe, maybe. In the standard formalism of quantum mechanics, one usually just imagines that all one can determine are probabilities for different histories or different outcomes. But this has made it something of a mystery why we have the impression that a definite object really seems to exist. One possible explanation would be that at some level a branch of reality exists for every possible behavior, and that we have just experienced the branch that our thread of consciousness has happened to follow. But that's really many worldish, isn't it? A multi-way system. Oh, that's from the new kind of science book. Oh, look at these many was interpretations of quantum mechanics. Yeah. But our models immediately suggest another, more complete and arguably more scientifically satisfying possibility. In essence, they suggest that there is ultimately a global objective reality defined by the multi-way system, and it is merely the locality of our experience that causes us to describe things in terms of probabilities and all the various detailed features of the standard formalism of quantum mechanics. We will proceed in two stages. First, we'll discuss the notion of an observer in the context of multi-way systems and the relation of these to questions about objective reality. And having done this, we will be in a position to discuss ideas like quantum measurement and the role that causal invariance turns out to play in allowing observers to experience definite, seemingly classical results. So this is like this goes straight to the spookiness of, or to the weird parts of quantum mechanics, I guess, rather than just having an introduction to other concepts. But it's just introduction, so we'll see. So how might we represent a quantum observer in our models? The first key point is that the observer, being part of the universe, must themselves be a multi-way system. And in addition, everything the observer does and experiences must correspond to events that occur in the model. Okay. This latter point also came out when we discussed spacetime, and we concluded there that it meant we only needed to consider the graph of causal relationships between events to characterize any given observer. We then just had to say how the observer would sample this causal graph. Typical example in studying spacetime is to consider an observer in an inertial reference frame, which corresponds to a particular foliation of the causal graph. But in general, to characterize what any observer will experience in the course of time, we need some sequence of space-like hypersurfaces that form a foliation which respects the causal relationships and thus the ordering relationships between events defined by the causal graph. That is really dense. um, so these are foliations, I guess. But now we can see an analog of these in the quantum mechanical case. However, instead of considering foliations of the causal graph, well, we need to consider now foliations of the multi-way graph. Like I feel that this is really like so each of if I imagine A and B being zeros and ones, like I do feel like that's some sort of like each of these foliations would correspond to a wave function, right? That tells you and probably you can calculate probabilities if you just kind of count the paths or something. So if I stay here, I'd have 50% probability of ending up in the AA state and 50% probability of ending up in the ABB state. So these would be these would be the wave function, I think. Uh, in the course of time, the observer progresses through such a foliation, in effect, at each step observing some collection of states, with certain relationships between them. A different observer, however, might want to sample the states differently, and might effectively define a different foliation. Okay, what does it mean? Hmm. Does this have anything to do with the basis idea? But then that would correspond to a different foliation. This means a different cutting of this multi-way system. One can potentially think of a different foliation as being a different quantum observation frame or quantum frame. Is it quantum frame the thing with the like the Z like quantum observation frame? A quantum reference frame. But I mean already I like the fact that this so some of the concepts start to pop up and then for me it's going to have to there's going to be a lot of work trying to map these things and trying to understand what I'm learning and whether this makes sense or not. A quantum reference frame which is treated quantum theoretically is an abstract coordinate system which defines physical quantities such as time, position, moment, spin, and so on because it's treated within the formalism of quantum theory, has some interesting properties which don't exist in normal coordinate. No, that is not. I don't think that is the axis, but or maybe yes. Ah, yeah, okay. So that Z would be a reference frame is implied. It can be understood. Yeah, yeah, yeah. So if I'm in the Z basis, that's one reference frame. If I'm like in the X basis, that's another reference frame. I think that's what this means. So this would correspond to different foliations of the graph of this multi-way system. For example, if I imagine this being zeros and ones, right, and that's like a Bell state, which you have 50% probability of observing, say, 0, 0, and 1, 1, like say it's a two-qubit system. From if I change the reference frame, if that is the right thing to do, right? So you observe these, but then if I do that, would you're basically it's basically the same, isn't it? Mm. There's no other foliation you can. Okay, but I think I start to kind of connect some of these things. In the case of something like an inertial frame, one is likely to find how an observer will be sample different parts of space over the course of time. In a quantum observation frame, one might have a more elaborate specification, sampling particular states of relevance to some measurement or another. But the key point is that a quantum observer can in principle use any quantum observation frame that corresponds to a foliation that respects the relationships between states defined by the multi-way graph. And this has a meaningful notion of time. Okay, so you cannot pick any foliation. There's some restrictions to this. In both space-time case and the quantum case, the slices of the foliation are indexed by time. So I guess like 1, 2, 3, 4. I guess so. But while in space-time case, a slice corresponds to space like hypersurface, the space in space. In the quantum case, each slice corresponds to what we can call a branch-like hypersurface that spans not ordinary space, but instead the space of states, or the space of branches in the multi-way system. But even without knowing the details of this space, we can already come to some conclusions. In particular, we can ask what observers with different quantum observation frames um, and the different choices of branch-like hypersurfaces will conclude about relationships between states. And the point is that so long as the foliations that are used respect the orderings defined by the multi-way graph, all observers must inevitably come to the same conclusions about the structure of the multi-way graph, and therefore, for example, the relationships between states. Different observers may sample the multi-way graph differently and experience different histories, but they are always ultimately sampling the same graph. One feature of traditional quantum formalism is its concept of making measurements that effectively reduce collections of states. What is quantum formalism? Like, is the mathematical formulation of quantum mechanics. Reduce collection of states as exists in a multi-way system to what is basically a single state analogous to what would be seen in a classical single path evolution. I guess what this means is just the measurement itself, right? From the point of view of quantum observation frames, one can think of such measurements as being achieved by sculpting the quantum observation frame to effectively pick out a single state in the multi-way system. Okay, what is this? So these are different foliations. We will discuss this in more detail below, but the basic idea is as follows. Imagine that our universe is based on a simple string substitution system, such as A is replaced by AB. If we start from a state AA, as in the picture above, the multi-way evolution from this state immediately leads to multiple outcomes associated with different updating events. But let us say that we just wanted some kind of classical summary of the evolution, ignoring all of these different branches. One thing we might do is not trace individual updates, but instead just look at generational states. Oh, that goes to chapter 5. Systems like cellular automata always update every element at every step in their evolution. But in string substitution systems, as well as the presence of overlaps between possible updating events typically means that there is no single consistent way to do this kind of parallel updating. Nevertheless, in studying our models in earlier sections, we often used steps of evolution in which we updated as many elements as we consistently could. And we can also apply this kind of generation-based updating to string substitution systems. Meaning that each level is a generation, or in which all updates that can consistently be applied together have been applied. Okay, and with the particular rule shown here, we then get the unique sequence of states highlighted above. Why? So these are the states in which if we apply all the rules together. Okay. So, I get it. So from AA, applying all the rules together consistently will lead you to the ABAB case. Oh, okay, that's tricky, right? Because you've basically, if you just consider the application of one rule, indeed you've got two possibilities, which then leads to, of course, three possibilities, one of which is this one, which is kind of consistent with this concept. of generational updates. Okay. So this is the red states are those states where, in the previous one you've applied all the possible rules, and here you've applied all the possible rules as well. Okay. And as we'll discuss below, we can indeed consider these generational states as corresponding to definite classical-like states of the system that can consistently be thought of as potential results of measurements. What? Okay, you lost me there, I think. Is it that you always get a unique sequence of states? Yeah, okay. But I'm not so sure, because it could be that you have a rule set that can have multiple, that can have more than one, um, you know, set of generational updates, in the sense that, like, consistently you can apply maybe 5 of the 6 rules, say, at the same time, or another subset of 5 rules from the same 6 rule set. In which case you wouldn't have a single updating sequence, would you? But now let's imagine how this might work in something closer to a complete experiment. So we're running the multi-way system shown above. Multiple states are being generated, but at some moment, we as observers notice that actually several states that have been produced, say ABBA and AABB, can be combined together to form a consistent generational state, ABBABB. That is that ABBA and AABB? ABBA and AABB. Why? But even though these states ultimately had a common ancestor, they now seem to be in different branches of history. But now causal invariance makes a crucial contribution, because it implies that all such different branches must eventually converge. And indeed, after a couple of steps, the fully assembled generational state appears in the multi-way system. To us as observers, this is, in a sense, the state we were looking for. It is the result of our measurement, and as far as possible, we want to use it as our description of the system. Okay? These lost me a bit right now. Like, so far, the way that I think this maps to a system is that each foliation is really the state of your system at a given time, which will be the analogous of the wave function. That seems to make sense. But this unless this generational state stuff has got to do somewhat with averages, or like expectation values or something. I don't know. Where was I? And by setting up an appropriate quantum observation frame, that is exactly what we can do. For example, as illustrated in the picture above, we can make the foliation we choose effectively freeze the generational state, so that in the description we use of the system, the state stays the same in successive slides. What? But it doesn't stay the same. The structure of the multi-way system puts constraints on what foliations we can consistently set up. In the case shown here, it does allow us to freeze this particular state forever. Oh, I guess what they mean is that, okay, I get it. So the foliations are like going this way. And so you set up the foliations in a way that these states are never reached. But how can you do that? The structure of the multi-way system, okay, yeah. Um, and as we will see later, this kind of spreading of effects in the multi-way graph is closely related to decoherence in the standard formalism of quantum mechanics. Okay. In what we just discussed, causal invariance is what guarantees that states the observer notices can consistently be assembled to form a generational classical-like state that will always actually converge in the multi-way system to form that state. But it is worth pointing out that, as discussed in 121, strict causal invariance is not ultimately needed for a picture like this to work. Recall that the observer themselves is also a multi-way system, so within their consciousness, there will usually be many simultaneous states. Looked at formally from the outside, the observer can be seen to involve many distinct states, but one could imagine that the internal experience of the observer would be, in effect, to conflate these states. Causal invariance ensures that the branches in the multi-way system will actually merge, just as the result of the evolution of the multi-way system, but if the observer experientially conflates states, this in effect represents an additional way in which different branches in the multi-way system will at least appear to merge. Formally, we can think of these in analogy to the operation of automated theorem proving systems. It's like the observer adding lemmas that assert the equivalence of branches, thereby allowing the system to be completed to the point where relevant branches converge. So the observer can just define that certain states are equal, and that's it. Independent of whether there is a strict causal invariance or not, there is also a question of what kinds of quantum observation frames are possible. In the end, just like in the spacetime case, such frames reflect the description one is choosing to make of the world. In setting up different coordinates, one is effectively changing one's description and picking out different aspects of a system. And ultimately, the restrictions on frames are computational ones. Something like an inertial frame in spacetime is simple to describe, and its coordinates simple to compute, but a frame that tries to pick out some very particular aspects of a quantum system may run into issues of computational irreducibility. And as a result, much just happens in connection with the second law of thermodynamics. There can still, for example, be elaborate correlations that exist between different parts of a quantum system, but no realistic measurement, defined by a computational feasible quantum observation frame, will succeed in picking them out. Okay, so I guess that was the introduction, probably, right? 8.12. Oh, sorry, not the introduction, but like the basic concept of quantum mechanics. So, but there's to some extent a couple of things that kind of seem to make a bit of sense, right? So we we're talking about quantum systems, and we're talking about their evolution in time. And so what this is trying to do is trying to, so you have a model that tracks how the system changes or how the system can change, which effectively, I mean, I like this because it actually really to somewhat relates to my work with the ANSYS library, which is essentially if you have essentially that's what the wave function is telling you. Is like the wave function is telling you your system is in a linear combination of multiple states, right? And they have a probability associated to it. And that seems to make sense. What I don't yet grasp here is the whole concept of the generational states. Because if I map each foliation to if you would make each foliation be an analog of a wave function on, with a given basis, at the z basis, right? Like I don't know what that is. And so generation. So this is the graph constructed by the product, the production of new hypergraphs, or sorry, of new strings on the application of one of the transformations. But we can consider, okay, the generational multi-way graph, in which we do as many non-overlapping updates as possible on a given string. For this particular rule, doing this straightforward, since every A and every B in the string can be transformed separately, but the result is now a radically simplified multigraph way. There's just one single path forward. The generational steps here involve an increasing number of updated events, as we can see from the rendering of the evolution. So all the states within the generational states will appear somewhere in the full multi-way graph, but the full graph also contains many additional states, and among other things can be thought of as representing all possible intermediate states. For a rule like these, okay, that's what we have. Yeah, okay, good. So it's not always the case that the traditional multi-way graph involves just a single path. So this rule would generate this graph, but then the multi-way graph. Okay, the generational multi-way graph. Oh wow. Okay, I get it. Is always, in a sense, a compression of the full multi-way graph. And one way to think of it as being derived from the full multi-way graph by combining sequences of edges when they correspond to updating events that do not overlap on the string. But there's also another view of generational evolution. Consider a branch graph from the full multi-way graph above. This branch graph is derived from the layered foliation shown. So the first applying different rules to a single part of a string. The second highlighted different parts of the string. Especially disjoint events. What are branch graphs then? But I don't see how this is anything to do with measurement. That's kind of what they're definite classical-like states of the system that can consistently be thought of as potential results of measurement. Let me try to do one just small thing, right? So let me just open Paint. So if I have a 2-qubit system, right? I guess, Okay, so I guess what because I think I know where this I think I can try to make an analogy here, which is sort of if you've got a circuit like 2 qubits, right? And I apply the Hadamard gate. God, that's the ugly Hadamard gate. And so that's the plus state and the plus state, which basically, um, it means the state of the system is the basically this state of the system, right? But what I've done here is I have applied these kind of uh, unconsciously as a one single thing, but in reality, each operation could be thought of as being applied differently. So my system is like that, and I could imagine that the updating rules of my system are turn a zero into zero plus one, and turn a one into a one zero minus one. These are really the rules in this case, and so I could as well just that. Look at these. Okay, so if I start here, so I have more space, 0, 0, right? I can apply the rule on one side and say, that is the 0 plus 1, 0, or I can apply the rule on the other side, 0 plus 1. And now I get it. Okay, so this is more, uh, so this is a bit more complicated because then now I can have, or let's say that's the only rule is no, not this one, just this is the only rule, right? So now here I can either have a 0 plus 1 plus 1, or I can have a 0 plus 1, 0 plus 1, right? And the same, like, yeah, okay. So these are the generational states. So what this is basically telling me is that there's certain states I don't really care about, right? Because if I'm thinking of the evolution of a system and I'm thinking about these, so-called moments, so to say, um, like these are time evolution steps, right? And I just really, so if I think about a foliation and, these being a foliation, in reality, all this kind of stuff, like this one here, right? Like these. It's stuff I shouldn't care. At the end of the day, I only care about the state where all the rules have been consistently applied. Mm, I'm not entirely sure that I get it, but it feels like because there's one thing that still does not make sense, which is the way that this is put in here, that these things can be then classically observed. It's not you can classically observe that. It's not that that's the result of measurement. So that's why I'm like, I can't see the concept of the generational evolution concept. Um, okay, but I guess I need to sleep on this. It's been already uh, 1 hour. Yeah, quantum formalism. What is in what is waiting for me after these? That's going to be a long journey. But so this was the very very basics. I mean, not that bad to be honest. It's about evolution of systems, right? So quantum mechanics is about like yeah, it's just that's really it. That's not a bad starting point, right? So you start with taking a look at systems and how they evolve in time. It's just that in this case, we have a model that tells you that the way a system can evolve is it, there's different rules for evolving. It's just that you kind of can consider all the possible ways in which the system is evolving, and that kind of builds these multi-way graph here. But not everything that is in here makes sense, right? So then there's also the whole generational concept here that I'm still not so sure I map correctly. But then you've got the foliations, which are like the time steps. Cool. And quantum formalism, this is going to be, let's just take a quick sneak peek, right? But it's the same following multi-graph system. Each state in the multi-way system has some quantum basis state. Oh, oh yeah, okay, makes sense, right? As I said, each is a basis state. Well, how can you get more basis states? That's weird. It's a basis state, right? So if you've got one qubit, then you've got two. Okay. An important feature of quantum state is the phenomenon of entanglement, which is the phenomenon of connection correlation between states. In our setup, that is basically a reflection of common ancestry of states in which, in the multi-way graph, interference can be seen as a reflection of merging, and therefore common successors in the multi-way graph. Ah. But this seems to be a bit of a more general concept because this what this is basically telling me is that this system is growing in terms of basis states, which is something that I have not seen before. If each node, if each state in the multi-way system is some quantum basis state, right? We start just with one basis state. Okay, probably you would probably think maybe that all the other ones are zero. So effectively, one way to map that is like 1, 2, 3, 4, 5, 6, 7, 8. So let's imagine that will be a 3-qubit system. So you have 8 possible states. It's just that you start with just one of the basis states and then you're populating the other one. So that will be from one basis state to another basis state. That's a totally different basis state, right? So this could be the state 1 or 2. So yeah. And then that takes you into a superposition of two different states. But still, and what they're saying is that this is then reflecting entanglement. Is it though? Couldn't it just be a superposition? Because the superposition doesn't have to be entangled, right? Hmm. Given a particular foliation of multigraph, we can now capture the entanglement of states in each slice of the foliation by forming a branchial graph. Okay, that's going to be more interesting. It would be cool to play with these. Actually, I might, before just jumping into these, I might as well just try to get set up the whole cloud thing. Mm. Where was that? Software tools, that's where I was. Oh, there's a model implementation in GitHub. That's cool. Uh-huh. Okay, so you can actually get that. Oh, that's cool. Okay, that's something to take a look at. Where did I find the... Wolfram Cloud, sign in. Can I just register? create one. Wolfram cloud. Sign up for free. Okay. I'll do that maybe probably off stream. So oh, look at these. There you go. Install Wolfram desktop. Let's do that. Oh, I gotta upgrade. No, I don't have money. New notebook, my files, new notebook. 5 minutes, hands-on intro, some things to try. Okay, so this is basically, I can type here. Okay, cool. So you can actually literally type actual text. Okay. But I can, in theory, just copy these, right? So that's kind of copied, and then if I open it here, I can just paste it. Oh, shift, sorry. It's okay, so it's thinking. Oh, there you go. Okay, cool. Nice. So actually we can actually have a notebook. It's awesome that I can play with this stuff for free. That's awesome. Cool. So what happens if I just change these to like, I don't know, H. Boom. Oh, look at these. That's interesting. These actually leads to like hypergraphs which are not fully connected. Okay, that's cool. How much does it cost to upgrade? Is that expensive? Full technology stack, R&D. I don't know which ones are like. Okay, it takes too long to get the pricing. Whatever, next time. But I'm there. Okay, cool. So then I could images will be good to start. I can copy that to clipboard. That's pretty cool. So I can actually copy that. Oh, that's nice. Resource function, multi-way system, and then you kind of give it the rules and then the starting point and states graph, whatever that means. And so that's 5 steps evolution. And I can give it also 9 steps evolution. Oh God. That is definitely more complicated. Can I render this in a nicer way? I can make that bigger, but that doesn't make any. God, that is a mess. But look at these. It seems like it's converging to some kind of like, I don't know. I don't know. But anyway, it'll be nice probably to follow along. Cool, but it seems like at least at least I think I have it a bit more structured in my head right now. So I understand. So we're talking about states and we're talking systems and states and how they evolve, and then the way they map this is each node it's a base state. So if that were a quantum system in a quantum or quantum circuit like in a quantum computer, then I'd say okay, we've got like I don't know how many qubits I have, right? That's the thing. It's like this is just you've got an arbitrarily large amount of qubits, which kind of it's a nice way to think about it, right? You're not constrained by the amount of qubits, but you're like, um, you're just rather evolving the system. Okay. Um, yeah, cool. A lot of new stuff. See you next time. Probably next week. We'll see. But I'm liking that. I'm liking that. Yeah. Bye bye.